Welcome to A-Tech Training's Quick Start video series. Today we're going to be featuring our electric vehicle systems trainer, model 5820 EV. We're going to go over the parts and pieces that make up this unit, explain how to wire it together, and show how you can implement it into your classroom training sessions. So go ahead, grab your operations manual, and let's get started. Now that we have our trainer completely wired up, let's take a look at a few operations. First of all, our ready up switch is right here. So when I click this switch on, it's going to use our 12 volt system. It's going to activate our high voltage contactor, which is going to bring alive all of our high voltage systems. So our high voltage battery is passing power through the HV circuit protection, sharing that power in the junction block, and then from the junction block it's being divided up to the DC to DC converter, and then over here to the DC to AC inverter. So we've got high voltage coming in, 120 volt AC coming out. We also see down here our conversions happening. We're running about 26 volts in our high voltage battery pack. We're stepping that down to just under 12 volts. That's a safe voltage for our smart battery management system. And then this unit, as we see, it's red here, which means it's detected that our low voltage battery has a lower state of charge than what it wants to see. It's looking pretty good on our scale. This thing is top notch here. It's going to fill this battery all the way up. If we look over here on our low voltage side, we have our simulated body circuits. Our tail lights are on, our headlights are on. Everything is protected by a simple blade fuse here. And we do have our junction block that's allowing us to spread our power out so we can supply power to our high voltage contactor. If we notice up here in the top left hand corner, this is our charge contactor assembly. And this unit is designed to separate out or isolate the entire system just so it can charge the high voltage battery. So if we were bringing this vehicle into the garage, I would turn the vehicle off. I would go out to my level 1 charger, which is running at 120 volts, and I'm going to plug my charger into the wall. And then I'm going to take my umbilical cord and I'm going to plug that directly into the battery charging port on the trainer. And then I would plug this directly into the wall. And when I do that, this LED light will come on to let me know the state of charge. When it's red, that means the unit needs to be charged up. When it turns solid green, then that means the unit is completely charged and ready to be driven down the road. So our charge contactor works very similar to an actual electric vehicle in that it's going to isolate the car out so the vehicle cannot be driven while it's plugged into the wall. This is very, very important. Everybody may have seen someone drive down the road with the gas pump hose hanging and dangling out of the side of the car. We certainly cannot do that when we're hooked up to our house power or to a fast charge station somewhere out on our commute. So now we've had a chance to see how the charge contactor and the level 1 chargers works on our trainer here. Now we're back to our electric vehicle system trainer. You'll notice we've removed all the components except for the high voltage junction block and the low voltage junction block. Both of these units exist in a different variety of formats depending on what type of vehicle you're working on. Our Nissan Leaf, the high voltage junction block, is located inside of the battery pack itself, and the low voltage junction block can be found underneath the dash and underneath the hood. These units are varied in different locations, and you might even have an external high voltage junction block if you're working on an electric vehicle that's been converted, maybe like a classic car that's been converted over to electricity. We often find these high voltage junction blocks exterior of the battery pack assembly itself. It's important to have the conversation with your students that we have traditional 12 volt circuitry. It's going to run power and ground, and then our ground will be run back through the chassis of the vehicle. On our high voltage side though, we need to make sure our students understand that both the positive and the negative side of all the high voltage wiring are going to be colored in the orange color, and that the negative side of the high voltage system does not run through the chassis ground. This is done for circuit integrity checks and it ultimately leads to a safer operation for the user of the vehicle. We have on display a couple different types of circuit protection that would be found on today's electric vehicles. On the right-hand side, we have our low voltage circuit protection. It's a typical blade fuse that we would find on any car or vehicle, or basically anything that's running electrical circuits in it today. And we could test this unit just like we would on our traditional cars or other electrical training. We can go right to the top. We can test either test point to show continuity between the fuse. If this was actually in the vehicle, we could do voltage drop over those 2 points or available voltage on either side. That way we can ensure that the low voltage circuit protection is in good shape and its integrity is good. On the other side, we have our high voltage circuit protection. These are typically ceramic based fuses that are fast blowing, kind of similar to what we might find inside of our multimeter. These are located on cars, depending on the manufacturer, in a wide variety of different areas. They can be found inside the service grip plug, they can be inside the battery pack itself, or they could be inside of a computer that controls the battery pack. It really just depends on the manufacturer, so you're going to want to reference the factory repair manual before seeking out where and how to remove those fuses. To check these fuses, most repair manuals do have simple instructions for just doing the same type of resistance check across the fuse. And if we noticed here from one side to the other, our meter is saying OL, showing OLs, meaning that this fuse does not have any continuity between it. So if we were to take this fuse out, get us another fuse and replace it, and then we could recheck to verify that our repair has been made correctly. We can go right back on that fuse and notice that we now have continuity, so that fuse is in good shape. Well, when would we obviously, if we have low voltage circuit fuse problems, we most likely have either a component that is overdrawing the current, or we have a wire that is shorted to ground. A high voltage protection fuse typically only blows when there's been some sort of collision. So if you've got cars coming in from the body shop, or cars that have run over things on the road, or had any sort of undercarriage contact where there might have been some integrity of the floor wire compromised, those type of situations can blow the high voltage protection fuse. So if you have a car that comes into the shop and it is completely powered down, showing no signs of life whatsoever coming out of the battery pack, it might be a good idea to go ahead and look into the high voltage circuit protection and ensure that your fuses are in good shape. Let's take a moment to talk about contactor and contactor control. Contactor is just a fancy name for a relay. We've had this concept of contactors available in our industrial areas for many years, but we've only just seen it come about in modern vehicles since the onset of hybrid electric or full electric vehicle systems. Really, the only difference between a contactor and a relay is the amount of voltage it's capable of handling. We have some simulated contactors available on our electric vehicle systems trainer. I'm going to give you a basic rundown of how it works. So I've got a small amount of current. This would be my low voltage. I've got a switch to control. If we want to think about this as my ignition switch right here, and I'm just feeding power into one side of the coil and ground to the other side of the coil. And once we energize the coil, it will create an electromagnetic field that'll close the contact between the high and the low side junction block over here. What you really want to convey off to your students is that there are a lot of different control features when it comes to an electric vehicle. We have to turn circuits on or off in a wide variety of ways. Contactors control a large amount of current at a large amount of voltage. And when we bring both of those units together, if I have voltage on this side and no voltage on this side, I'm going to get an excessive amount of arc. Now, I did do a live demonstration of this in a previous video, and we're going to go ahead and insert that clip now. One of my favorite instructor-led demonstrations that I like to use when talking to my students about contactor circuits and pre-charge circuitry is I like to explain to them in a real-world fashion about what happens when you bring high amounts of voltage and high amounts of current together in any given environment. And the best way to do that is to use a set of jumper cables and a simple fully charged lead-acid battery, and explain to your students that, hey, when I bridge an open in between two wires, one that's leading to a path to ground and one that's positive, this is what happens inside the relay or contactor. Okay, so we get a lot of arcing, we get some smoke coming off here, we got a lot of heat generated, and the reason why we have to have that pre-charge relay built into the contactor is so we can supply voltage to the ground side as well as have the voltage on the power side, so that way when we bring both of these units together, there's not a difference of voltage from either side. And when we do that, we don't get that arcing, we don't get that heat buildup, and we don't get that smoke that comes out through the process of bringing two high current, high voltage wires together. So as you saw in the previous demonstration, when you bring lots of current and lots of voltage together, a lot of sparks are emitted, a lot of heat is generated, and we use contactor control and a wide variety of relays to help prevent that from happening. On this particular setup here, when I energize the coil, we notice here we can see on the meter, now I have continuity between these two pins here. On an actual EV vehicle though, we're going to need to bring power to the positive side and power over to the other side of the contact in order to prevent that arcing from happening. This typically happens what we call our pre-charge relay. Now that we've gained a greater understanding of contactor control, let's take a look at another dynamic piece of the electric vehicle system. We've been talking earlier in previous segments about all the high voltage and how we can plug into the wall to charge our high voltage battery, but we haven't really talked about how do we generate power to charge our low voltage system. It would be nice if we could just take a wire straight from our high voltage battery pack and touch it over to our low voltage side, but unfortunately that's not how it works. We have to step down the power that comes out of the lithium ion battery pack, step it down to a more palatable level so that way a smart battery management computer can control the amount of current and voltage applied to the low side circuit here. So the way this works on our electric board is we go to our ready up switch and we ready our car on and we see our body electrical circuit comes on. When we do that, that activates the high voltage contactor, which goes ahead and supplies power from the high voltage battery pack to anything that needs it via the junction block. Right now I only have the DC to DC converter hooked up here in the middle. ATEC was very gracious enough to include two built-in voltmeters so we can visually see what's actually happening inside this DC to DC converter. As we can see, our high voltage battery pack is supplying just under 26 volts of power. The converter itself is stepping that down to 11.8. So 11.8 is going to be a much more palatable power source for our smart battery management system. This 11.8 will power up the battery management system, which will again charge our low voltage battery system here. So we can see if our battery monitor that is trying to charge it all the way up to the top. Most of your DC to DC conversion is happening inside of the vehicle itself. Most of these units are built into the power delivery module or directly into the traction motor assembly itself. But depending on the manufacturer and what accessories you have, you might find DC to DC conversion happening elsewhere, potentially in the air conditioning system, maybe the electric power steering system, or other additional systems, but it really just depends on who manufactured your electric vehicle. So we've been previously discussing the DC to DC conversion, which was found inside the power module and the traction motor. They're all built together on the Nissan Leaf that we've been looking at. We want to take this thing to the next step where we're going to talk about the DC to AC inverter. And on our electric vehicle systems trainer, we do have our DC to AC inverter. I'm going to give you a basic rundown of what's going on here. So we've got our high voltage battery pack here going through our circuit protection. We're going to be activated by the high voltage contactor. That's activated by us readying up on this switch over there. Once our contactor is closed, then power is supplied to the DC to DC converter, and also high voltage is supplied to the DC to AC inverter. This unit usually has two main functions. One is it takes the high voltage DC power that comes out of the battery pack and converts it, or I should say inverts it, into a AC signal. This particular unit converts 24 volts on this side to 120 volt AC at 60 hertz on this side. We're getting a nice AC sine wave that comes out that's going to drive our permanent magnet synchronous AC traction motor that we've got right here. So this is basically a very, very small version of what we would find inside of this Nissan Leaf or other potential electric vehicles that are out there on the market. Now, I do want to preference that not all the electric vehicles run AC motors, but it seems that a large majority of them do. But it is possible that they can do some DC motor control through the inverter. So the inverter, step one was to invert the DC to AC. Step two is it's going to actually control the traction motor itself. So the inverter gets signals from the vehicle control module, and those signals are interpreted to determine how much torque and power to apply to the traction motor. So two main purposes inside of this unit: taking DC, inverting it to AC, and then supplying the correct amount of power at the correct phase to the AC traction motor based upon all of your customer inputs. Before we look at some troubleshooting techniques on the electric vehicle, I want to take a moment to talk about the lithium-ion battery pack. Typically, most electric vehicles are using some sort of solid-state battery or lithium-based battery pack, and there are some concerns for overheating or the battery's getting too cold. There's some charge concerns. There's a lot of unstable things about lithium-ion batteries that need a complicated computer control system to ensure that everything remains safe. On our 5820 board, we do have a simulated high voltage battery pack, but our battery chemistry in this battery is nickel metal hydride. It is comprised of 20 different cells that produce about 1.2 volts, and each cell has about 2200 milliamp hours of capacity. So the combination of all these different cells stacks up in order to get our total high voltage output, and then our milliamp hours is basically going to be how long we can actually use this battery given a certain amount of current draw on it. If you also notice on top, we have a stated charge indicator. So by simply pressing a button here, we can get an immediate stated charge of our of our high voltage battery. Notice we're running about 50% right now, so we have been running this unit quite a bit today. Also built into this unit is a temperature sensor, so if the battery pack was to get too hot during the charging process, it will actually stop the charging process completely to prevent any damage happening from the batteries, the cells, or to the trainer itself. Couple things we want to mention: that this is different than the battery we're going to be looking at on the Leaf. The battery on the Leaf is a lithium-ion based. It has 192 cells and produces approximately 360 volts and has a capacity of about 24 kilowatt hours. So it is a substantially larger, beefier, and more powerful battery pack than what's on our simulator. But notice we don't have to wear any special gloves. Everything is very safe to work on here. If we wanted to work on the lithium-ion battery pack, we would definitely need to be wearing all of our proper safety PPE in order to do some exploration. One other additional component that I do want to mention is inside of the Leaf's lithium-ion battery pack is a lithium-ion battery controller. Due to the sophistication of this unit, it does need a computer that is installed directly into the battery pack near one of the module stacks. And the lithium battery controller is the core of the battery control. It detects the voltage and current of the assembled battery. It detects the temperature of each module and the voltage of each cell to judge the state of charge. It also calculates the possible input-output values. It meters indication values and also chargeable values, and sends all this data to the VCM, or the vehicle control module, and then that module controls the vehicle according to the battery state. Thank you for joining us today as we went over our electric vehicle system trainer, Model 5820 EV. We hope you enjoyed learning about the parts and pieces that make up an electric vehicle system. If you found this training intriguing, please make sure to hit the like button. Also check out our other social media pages on Facebook and LinkedIn. And don't forget, we do quarterly training here at ATEC if you'd like to learn more about your equipment and how you can use it further in your classroom. Thanks a lot and have a great day.